and you're gonna need to load the P module, which includes the Vampir. So while we're waiting on a couple of people from the others, are there any questions? Like, I hope you all had created a trace yesterday, and now you should go to the trace directory, so to the nest parallel benchmark, and to the bin.p directory where our traces are. And within that directory, after you have loaded the tooltip and after you have loaded the P module, all you still have to do is to run Vampir and use the traces.otf2 file within your trace directory as an input. And that should start the Vampir user interface. Yeah, you can just start the view. Oh, I see. Right, so if you start Vampir without any trace on the command line, we'll just give you a GUI to ask to select a local trace. Okay, so once you've opened that, you will see like the standard display. So we have the main timeline here on the left, and Brian is running increase the font size. I think it's already at 12, so it's already pretty applicable. So we have the main timeline display here on the left side. We have one of the summary charts here with context view, which gives us a context of what we have clicked on, a function legend, and a toolbar on top. That's pretty standard. Okay, so if you would have started it without any OTF2 input, it would ask you if you want to open any of the recent files or select any OTF2 trace or OTF1 trace from your local machine. Or if you would have Vampir server, you could also ask it to open it on a remote system. It has said there's a master timeline, a couple of different displays. I'm going to go into detail into those. And there's what's called the navigation toolbar, which always gives you a total temporal overview over your program, in contrast to the other displays, which can be zoomed into and selected only a portion of the processes or a certain time slice. The main timeline display gives you detailed information about functions, the communication, synchronization events for all your processes, threads, and accelerators. So we see all the different events, and it's going to be more clear if we zoom into those, colored differently according to this function legend down here. So for example, NPI events will be dark red. In that case, OpenMP events will be anything from brown, green, bluish, another color shade of brown, and normal application or user code will also be some kind of greenish color here. So Vampir tries to come up with full of colors for different paradigms, so for OTF2, or for different parts of OTF2, like synchronization or parallel loop. But you can also change all of these colors. You could also change it to whatever other color you would like if those don't appeal you, or if you would like to be them more different, or if we come to separate functions, we could also select one function and give it a special color, but we don't need to do that right now. Here on top, for example, we have what's called timeline, of course. So we see our program started at 0 seconds, obviously, and it ran about 30 seconds. Exactly, it ran 30 seconds and 533 milliseconds. And here we see the total information for all processes. And if you click on, which is like the first symbol here, so we could also have a second instance of that display if you want to. If you click on the second display here, on the second icon here, it will open what's called the process timeline. Yeah, just press harder. So it will open a second display, and you could also close them all here with this small X button. You could detach them from this window with the arrow button, or you could also if you want to make it full screen or go somewhere else, have a deeper look into that, and we could reattach it using the arrow button again. And we can also change sizes, of course, or move displays around however we would like it to be. And what we see in this process timeline, for a certain selected what's called location in the Vampir terminology. So a location could either be a process thread, accelerator thread, or whatever. We see the full call stack here. So we see that on the first call stack level, obviously main ran all of the time, and then like the quad run version of main here, and then main called the iteration loop a couple of times. And if you would click on any of these, you would see that this is actually not one function, but different instances of iteration. And whenever you click on anything here, you see it appearing in the context view. So you see when did this function instance started, when did it end, what's the duration, on which location is it. So this one is on master thread 0, for example. It's a function. To which group does it belong, and so forth. And then we see that the call stack goes further down until we go into OpenMP at some point. And we have the OpenMP parallel here, and within the parallel, or the do's, the OpenMP do loops, and within the loops there are certain inputs. Since these synchronization functions, for example, are very small, we might want to look into one of any of those in more detail by zooming in. And zooming in can be done with the mouse wheel, but you could also select a certain time frame just by left clicking and dragging your mouse. And you would going further, it tells you, so the time changes, it tells you which time you have zoomed into. Now we see the more detail of each iteration, for example. Yes, you can also zoom vertically. You can, I don't think you can do that here, but you definitely can do that here, which might make sense or not. So if you have more processes here than fit in your display, like right now, what you can do is you can right-click here. You can go to Adjust Process Bar Heights, and you could do Fit Chart Height. And then it will collapse all of those that you have into whatever the size of this display is. However, since we have less pixels, you might have fewer pixels than processes. If you have to deal with a real big number of processes and threads, not all of them might be visible, and that's going to be anti-aliasing. That's what I meant in the beginning. The visualization of a very big program is a big challenge by itself, and a whole discipline by itself. And we can revert any of those actions by, for example, right-clicking in the display again, and could adjust the process bar height, the text height again, and we could also, if you right-click once more, we could also reset the horizontal, so the time zoom, or the vertical zoom, which is the spatial zooming. Yeah, with this particular trace, you can see there seem to be like two phases, which are pretty typical for HPC programs. There seems to be an initialization phase in the beginning, which is mainly the MPI init here, and there seems to be a computation phase. So we can have a look at how balanced the MPI init is. It seems to be fairly balanced, but unfortunately, as with every MPI program, it takes also a fairly large amount of time. But you could also see at which point our computation phase has started. What you can also do, if you don't want to zoom into something, but you just want to see, okay, how long on average is this phase, you can hold down the Shift key on the keyboard and then do the same zooming action, so left clicking and dragging, and it will just tell you what the time is without actually zooming in there. So if you just want to have an average idea of how long this MPI init phase is with a couple of different functions left and right, you might want to do that. Another, for my very intuitive, is you can also revert all the zooming and going into actions by just using Control-Z, like in your office environment or something. So if you zoomed into something, just you want to go out again, just use Control-Z, and still undo that action and go back one step in time. I think you can do Control-Y to redo that action. So now, could you go try Edit? Maybe it's different. I'll Control-Shift that here. And in the beginning it says it cannot be displayed because no performance event data has been selected, or it doesn't contain any performance event data. But we would want to display something anyway, so just right click into that display, and we can select the metric we want to display here. A metric is anything from, there are some, also let's say otherwise, there are some derived metrics that Vampir creates for you by itself, like MPI latencies, the message data rate, the number of messages and transfer. What do we have here? Transfer times, seems to number, simultaneous messages, exactly. Or for example, the time spent in MPI rate. If you would have collected the puppy counters, they would also show up here. Or if you would have collected a trace of energy counters attached, they will also show up here. Look at them. And maybe we want to have a look at what we select. For example, the time spent in MPI wait. And once we click at that, it tells us to select a measuring point. So maybe we want to have a look at what's this metric for our master thread 0 in the beginning. So we just leave that selection and click OK. And it tells you that this metric has a couple of peaks over time, and I think we should zoom out totally. Yeah, exactly. And if we zoom out to the full extent of our program, to the full 30 seconds, it tells you how that metric evolves over time. And there already seems to be quite a big of a peak here. And we could also zoom horizontally again, of course. We could also zoom vertically in that display if you want to have a look of how big the differences are here. And this peak already looks quite interesting. However, if you go to exactly, if you reset that, and if you go to select metric again, you might also want to have a look at how does it evolve, or how does this metric behave on any other thread, or possibly how does it behave as a summary over all measuring points, over all processes and threads. And to do that, we can click on that checkbox here, and select any number of threads or processes. But you could also select all of them by clicking on the topmost icon. Once you have done that, try OK again. And now it summarizes over all the processes and threads, and we see that this peak becomes even more significant, let's say. So maybe we want to have a look of what is happening here. So let's just zoom in there. So we're saying that's kind of a system noise here at that point, where our edge job was stalled for whatever reason. This is like very significant in contrast to all the other iterations. So we don't really see anything so far. Maybe we need to zoom in a little bit further in time. And now slowly becomes apparent that there's quite a store here. Further, you see, that's a wait all, which totally makes sense since we are looking at the time spent in MPI wait all. And it seems that those two processes are stalled waiting on the two others at that point. So what we see here is for one thing, the MPI function call, which Brian has selected here, so it's this red box. But we also see those black lines, and if you click on any of those lines, that's not a line, we see that's a message. So it's the actual MPI message that has been sent, and it tells you the message type, so it's point-to-point message, originating from master thread on process 1 to the master thread on process 0, and this message has a certain duration. It's telling you the MPI tag that has been used for that message, and anything else if you scroll down in the context view a little bit. Right, it will also tell you the data size that has been sent, and the approximated data rate from the size and the time, and the MPI communicator has been used. And we might want to click on this MPI communicator here, MPI com1, and it will tell you which processes are in this MPI communicator, for example. So whenever you see this kind of hyperlink here, you can click on that to look what's behind think if you click on it again, it doesn't really give you anything more. Okay, what else do we see here? We also see there's an OpenMP do loop over the threads of process 0. Okay, yeah, zoom in there, and it will. So there are other black lines here which are connected by those dots, and those are not messages. So if you click on any of those, it will select the whole frame and like shade it a little bit, and it will tell you that this is the implicit barrier over those 4 threads. And the implicit barrier started here and ended at this point, went over those 4 threads, and since though there's a little bit of load imbalance here between the do on the first thread, master thread, and the do on the other 3 threads, those were stored in an implicit barrier. And for example, Scalaska would have told us that automatically. It would have told, okay, those threads have quite some implicit waiting time here, while the critical path, if it should run over the first process, would have run over that thread, since that's the thread that's determining the execution time in that case. There's also the performance radar. And since the performance radar is pretty much like the counter data timeline, except that it shows the information always for what is shown on top here in this timeline display. So it shows you the metric over the whole range of currencies and threads. And here the MPI latencies metric is selected by default, and it's color coded. So you have the color bar down here, which is from very low values to very high values, according to which values are there in total, whole range of processes and time. And we see there's quite some impact here from this master thread, and might be interesting to look at it over the whole range of time. So let's right click and reset the horizontal zoom. And over the whole range of time, there's not too much difference here. There are only like 2 small peaks, but maybe there is more difference that we can't see in this shade of blue. Yeah, we can also do this. I think there should be a little bit of difference in color here, so it gets a little bit lighter here. It will also be easier to dimmer, but there seem to be quite some latencies here, which is where all the peak was. But if you want to have a closer look at how those shades of blue evolve, we can go down to this color bar, just drag it down to whatever range of information you want to look at. Yeah, so we might want to have a closer look at the lower values, and it will tell us, oh, okay, actually they're not the same value, all of them, but there's quite some difference, even though the difference are not so big that they show up if you look over it over the whole range of time. And you also see that the differences are ones over time, but there are also differences in spatial dimensions. So not all threads have the same amount of MPI latencies. Okay, we also try to zoom in already. Another very neat feature from my perspective is the find function. Of course, you might wondering, okay, now I'm looking at all those functions I have here in my profile, showing me the accumulate exclusive time for function, and there seems to be an OpenMP do called from this input file at line 301. And if I click on it, it gives me the context, but it doesn't tell me, okay, where actually is this function called in my program. And for that, you can go into that display. I think you have to click on it somewhere. Oh yeah, or either right click or press Ctrl F in the display, and you can start typing over here. So you could start typing, for example, OpenMP do, but we might also want to start with rhs.input, and it's going to filter those functions as we type. And I think you have to use .F :301. Okay, and now we got it. And if you click on this, now you can view enter. I see. And will actually tell us when this function is called. Apparently it's called all over our trace, but it might be that this function is only called 2 or 3 times, and you might want to find those. And if you zoom in again, or click at it, you see, okay, that's not actually one function call, couple of it, and it's just aliased, since we have to reduce all the time dimensions onto our small display. Here we tell us exactly, okay, this function has been called at that time slice. And you can also use this find functionality in other displays. So in the process timeline, for example, not only works here. Yeah, I don't think it's gonna work in all of the displays, only a couple of them. I don't really know to be sure, to be honest, what's the criteria on which display they haven't worked on. But maybe it doesn't make too much sense to have another coloring here, since it's color coded already anyway. Clicking works for all kinds of collectives. So the OpenMP barrier is a collective from the OpenMP perspective, but if you have an MPI barrier in there, so we can look at this in more detail. Okay, and what this one is doing is, according to the metric that has been collected, in that case accumulated exclusive time per function, it tries to aggregate or accumulate the processes and try to find out, okay, which of these locations, so which of these processes and threads behave similar to a process or thread according to the selected metric. So, for example, and it's a little bit like Scalaska. So this time frame, for example, determines what is shown here. Good. We set that. It's also going to be updated altogether. So we see that for most of the processes, there seems to be quite some similar amount of do loops, but then they differ on the amount of synchronization needed. For example, OpenMP synchronization. And apparently, Vampir thinks there are a group of 8 processes and threads that behave quite the same, and another group of 6 processes and threads, and so forth. So it's also a good idea to get an overview over what amount of metric, in that case, function runtime, is in that process or in that one. Yeah, that's the best color I could have thought of. But it definitely tells us more than if you have orange for all of them. Yeah, it's nice mechanic. Sometimes it's really interesting which colors Vampir seems to pick for you. They seem to change it with every new version of the program. It's always very interesting. Yeah, and we can color, for example, each function on its own if you want to differentiate even different functions from the group, for example. Yeah, I've already told you that the summary, for example, is according to a certain metric, and this display is according to a certain metric. So you might want to change that metric, but perspective of the program. So if you right-click the function summary, we could, for example, set the metric to be shown here, and it tells us a couple of available metrics. For example, the inclusive time, exclusive time, and the number of invocations. You might want to have a look at that one. Or like, yeah, could also clustering for a number of clusters. So I think by default it's automatic, so it tells you automatically reclusters according to the size of the system. Okay, so over on top here in the function for example. If you want to see any of those that have fewer function calls, like main only has 8 function calls since there are 8 processes here. And if you scroll down all to the top again, you will see that some of those are like truncated a little bit.